Okay, let's get started. So, hello everybody. Thank you for joining us today. So, welcome to the ASTRO ECR Astronomer in Australia seminar series. So, my name is Marianne Girard. I'm a postdoc at Swinburne University, as my co-chair is Amelia Fraser-McKelvey, and she's a postdoc at University of Western Australia. So before we begin, it's important for us to acknowledge the traditional custodian of the land on which we meet today. So the Aboriginal and Torres Strait Islander people were Australia's first astronomers, and we acknowledge their long-standing system of knowledge on which we continue to build. We acknowledge the traditional custodian of the unceded lands on which we are meeting today. So I'm speaking with you today from the land of the Yuhudjeri people of the Kulin Nation. My co-chair Amelia and our two speakers are joining us from the land of the Yadruk people of the Noongar Nation. We pay our respects to their elder past and present and extend that respect to all First people joining us here today. So today we have two talks. Each talk will be 20 minutes and we'll have 5 minutes of question at the end of each talk. So please save your question until the end of the talks. Feel free to use the chat function and you can write a question there and Amelia can read the question after to the presenter during the question session. So the talk will be recorded and they will be placed afterward on the Astro 3D YouTube channel. So by being here today, you also are agreeing to the Astro 3D's meeting code of conduct. So let's get started. Our first speaker today is Tristan Reynolds from the University of Western Australia. I want to apologize. There was a mistake in the abstract that was sent just an hour ago for his talk. So he will talk to us not about LIGO, but you can now share your screen, Tristan, and I'll let you present your research.
Great. So yes, thank you for that. So I'm Tristan Reynolds. I'm an Astro 3D postdoc at ICRA and the University of Western Australia. And today I'll be talking about some survey results from the WALLABY pilot survey, which, although I'm presenting this, there's more than just me who's contributed to this work. So also acknowledge that there's the wider WALLABY team has put in time and effort into getting to where we are now. There we go. So galaxies don't live all in the same environment. You have some galaxies that lie in the field and are pretty isolated without any nearby neighbors. Then you have galaxies which reside in groups. And then you have the galaxies that lie in the densest environments, which are galaxy clusters. And we know that the environment where a galaxy lies has a big impact on the properties of galaxies. So here just showing plots for 3 different ones. On the left, showing how the morphology of galaxies varies between galaxies in less dense, so in the field and low density group environments, so towards the left of the plot. And then moving towards the right, you move to those higher densities, particularly towards clusters. And as you can see, the fraction of spiral and irregular galaxies is largest when you're in low densities. And as you go to high densities, you end up with the majority of galaxies are your elliptical and S0 galaxies. Another property which varies, is affected by the environment of a galaxy is the star formation of a galaxy. And so in this case, at different redshifts, this is showing in the top right that galaxies in the field there's a larger fraction of galaxies in the field that are star forming compared to galaxies in the cluster core. And then in the lower right, that panel is showing how the gas fraction of galaxies, so the amount of gas relative to the amount of stars within a galaxy, varies with stellar mass. And in each of these different colored lines is different environment densities. So the blue is low density environments, moving down to red. So the bottom line is for high densities. And so as you can see, as you go to higher densities, the gas fraction also decreases. And this is across all stellar masses. And what is it that causes various properties of galaxies to be affected by the environment? Well, there's various environmental processes that act on galaxies. And here I'm just showing a nice illustration by Ari Chung, showing various environmental processes that act on galaxies that reside in clusters. And I'm focusing on what affects clusters, as that's what my work is the cluster environment. So you have harassment and mergers, which involve multiple galaxies. You have ramp, and then the rest of these properties involve the galaxy interacting with the environment. So ram pressure is basically a wind acting on the galaxy, which can strip off gas. You have turbulent viscous stripping, which is interaction between the gas and the intercluster medium. Tidal compression truncation, which is simply the tidal forces of the cluster itself going and removing gas from the galaxy. And then starvation, where there's no more gases getting onto the galaxy, and thermal evaporation, which is again the gases being heated up by the intercluster medium. So there's lots of different processes which act on galaxies within clusters. And one of the questions is how prevalent the various processes are on causing galaxies to change and evolve. And the aspect of the property of a galaxy that I'm focusing on is looking at galaxies in terms of their neutral hydrogen, or the H1 content. So H1 is detected by the 21 centimeter hyperfine transition, which is when the electron and the proton, when the electron flips its spin relative to the proton in the galaxy, which is a low energy state and releases a photon of energy at 21 centimeter wavelength, which we can detect with a radio telescope. And H1 is important because it's required for star formation by its conversion to molecular hydrogen. And it's also can be detected more easily at larger radii than the optical disk. So in the lower two panels I'm showing on the right, an optical image of NGC 7162 with H1 contours overlaid on top, which you can see extends much further than the optical disk. And this is also shown in the surface density profile for this same galaxy, where the gas shown in blue extends to roughly 23 kiloparsecs, while the stars extend only up to 15 or so kiloparsecs. And as a result, it means that the gas is a very sensitive tracer to looking at environmental processes affecting galaxies. And this is just very nicely illustrated for the M81 group, where on the left, this is showing the stellar light distribution for the group. And you see these three galaxies, which don't appear to be interacting or being affected by one another at all. But then if you look at the neutral hydrogen within the galaxies, you can see lovely tails and streams connecting all of them, showing that these are actually gravitationally interacting. So moving on to the survey I'm using. So I'm part of the WALLABY survey, which is the all-sky survey of H1 on the Australian Square Kilometre Array Pathfinder, which is an array of 36 dish antennas located out in the desert in Western Australia. And what makes this telescope cool is that it's fitted with phased array feeds, which means that we can observe a region of the sky at one time that's 30 square degrees in size. So that's much larger than most other radio telescopes can achieve. And right now we're doing the pilot survey, which is making sure that things are ready and that we can actually carry out the full survey, which will cover 3/4 of the entire sky, observing in H1. And for the pilot survey, we're observing 3 fields: the Hydra field, NGC 4636 field, and Norma field. Each of these is 60 square degrees in size. And the data I'll be showing is from the Hydra field, so the bottom left one shown here. So this field, although it's 60 square degrees in size, due to, as we're still testing things and all, the first set of data that we had to work with was a subset of this that was only roughly a third of the entire field, which was focused on the Hydra cluster, which I'm showing here the center of the Hydra cluster, indicated by the magenta star, and the virial radius by the dashed circle. And within the virial radius, we find 51 galaxies detected in H1, down to a sensitivity limit of 5 × 10⁻19 atoms per centimeter squared. Now, one of the advantages with ASKAP is that we're able to get for H1 a very high spatial resolution of 30 arcseconds, which is indicated by the orange circles in each of the panels on the left. So this means we're actually able to spatially resolve most of the galaxies we detect. And here I'm showing a resolved subsample of the 51 galaxies that are detected, which are well resolved, which in this case means that they're resolved by 5 or more beams along the major axis. And what I ended up looking at was looking at the asymmetry of these galaxies. So looking at, take the galaxy, rotate it by 180 degrees, and then sum the residuals. And if a galaxy is symmetric, its asymmetry will be very low, which is the case for the 3 galaxies in the bottom panel. The 2 galaxies in the top panel have very high asymmetries. And of these 2, one is located near the center of the cluster and is indicated by the red square. So right near the center on the sky, and also near the center in phase space. So that's looking at the velocity of a galaxy relative to the cluster center versus the distance it is from the cluster center. So that galaxy has a high asymmetry, and it looks like it's probably being ram pressure stripped. For one thing, if you look at the top side of the galaxy, the stellar disk extends beyond the H1 disk. So that shows the H1 is actually being truncated within the disk. And you see a bit of puffing out of the gas on the right side of the galaxy. The other one of the asymmetric galaxies lies right near the edge of the cluster, indicated by the blue diamond. And so this galaxy also looks like it's being ram pressure stripped, but it also lies in a very different part of the cluster to that galaxy near the center. And so I want to go and find out whether or not ram pressure is a feasible explanation for the observed asymmetric H1 morphology we see in this galaxy. So just in a bit more detail for this galaxy, so just showing a bit larger the integrated intensity map, so an optical image with the H1 contours overlaid. And shown here, I have taken a slice along the major axis of the galaxy, indicated by the red rectangle, and plotted the spectrum, essentially the profile we get along that major axis towards the southwest side into the northeast side in the bottom right panel. And here we can also see quite clearly that on the northeast side of the galaxy, that the H1 extends much further out than it does on the southwest side. So it's like there's quite clearly a tail out that side. And given this galaxy lies well out, like towards the edge of towards the virial radius of the cluster, it also has no nearby neighbors. So it's unlikely that its morphology is due to tidal interactions due to another galaxy. If we were to go and step back and not consider the resolved information, but just the integrated properties of the H1 deficiency, so the amount of gas it has relative to a similar galaxy in the field, and its flux asymmetry ratio, so that's taking the ratio of the flux in the right side, so the red part, to the blue, the right part of the galaxy, the integrated spectrum shown in the top right, we find this galaxy is H1 normal, so it has the expected amount of H1, and it's also very symmetric. So on the integrated properties alone, this galaxy doesn't appear to be particularly interesting or that there's anything going on with it. But once we resolve it, which is the power of ASKAP, we see that it does actually show signs of being affected by the environment in which it lives. So because it's spatially resolved, we can do some kinematic and mass modeling of this galaxy. So the kinematic modeling lets us go and measure the rotation curve of the galaxy, which we can see in the left plot. And then from that, we can go and do mass modeling to get an estimate of the dark matter mass at different radii within the galaxy, which we can see in the right panel, where we have on the top the surface density of the gas and the stars with radius, and then from our modeling, the contributions from gas, stars, and dark matter to that total rotation curve that we measure for this galaxy. And we find for this galaxy that it is dark matter dominated, which isn't unexpected. Many galaxies are. But from that, we can now go and look at the gravity and the ram pressure of the that could be acting on the galaxy to see whether or not ram pressure could feasibly be causing our observed morphology. So to do this, I use a very simple model, which takes the galaxy. It assumes it's moving face on through the IgM of the intergalactic medium of the cluster. And so the ram pressure acting on the galaxy is equal to the density of the intergalactic medium, and the, sorry, that's equation is wrong. It's supposed to be velocity squared of the galaxy moving through the IgM. So the density IgM, or the higher the faster the galaxy is moving through the IgM, the higher the ram pressure will be acting on this galaxy. And then the gravitational restoring force, which is keeping the gas within the galaxy, is measured using, is estimated using an NFW dark matter profile based on the dark matter estimates we made from our mass modeling. And for this, the results are shown on the right, and I'll step you through this plot. So this is showing the ratio of gravity to ram pressure versus at different radii out from the center of the galaxy. And gravity dominates if the ratio is above 0, because this is a log scale. So in the red region, gravity dominates and gas is retained by the galaxy. In the blue region, ram pressure dominates. And that means in the blue region, gas can be stripped from the galaxy. And I'm showing here.
Tristan,
yes.
you have 5 minutes.
Great, thank you. Yes, and here on the top panel, I'm fixing the velocity to 1,000 kilometers per second, which is roughly the velocity difference between this galaxy and the cluster center. And in the bottom panel, I'm fixing the IgM density and varying the velocities. And as we can see, that at the vertical dashed line, which indicates the radius of the leading edge to the bottom right of the galaxy, at all the different combinations of IgM density and velocity are below 0, so ram pressure dominates, which means ram pressure can indeed cause, does dominate and can actually remove gas up to that radius. There are, however, other environmental mechanisms that could be acting on the galaxy. As I mentioned earlier, tidal interactions and harassment are unlikely because there are no nearby neighbors. But other ones which are possible are viscous stripping and stripping by the cluster tidal field. However, I think these are likely less, contributing less to the observed morphology than ram pressure, because viscous stripping generally acts over longer timescales than ram pressure, and this galaxy is likely on its initial infall into the cluster. And stripping by the tidal field is most effective when you're near the cluster core radius, and this galaxy is roughly 11 core radii away. So it's well beyond the core radius of the cluster where ram pressure, where the strength of the tidal field will be weaker. So just my conclusions. I will note that this paper is currently submitted, so hopefully you'll see it on arXiv in the next couple of months. Hydra I is the first cluster that's been observed with WALLABY. And within the virial radius, we've detected 51 galaxies. And I will also note that this is the first time we've managed to reach WALLABY sensitivity in WALLABY early science and pilot survey observations, which is exciting. It means that we can it's proof that for our full survey, we will be able to go and be as sensitive as we thought we would. So ISO 501G075 is likely on its initial infall to the cluster, and yet it has an asymmetry that's very similar to one that's near the cluster center. And our modeling shows that ram pressure can produce the observed morphology, but there's also, we can't rule out small contributions from other processes like viscous stripping and stripping by the tidal field. And I will just end by showing you a nice picture of, as we have now gone and got the entire Hydra field processed and data distributed to the WALLABY team internally, this is showing all the galaxies that we've detected within the full 60 square degrees, which is roughly 270 H1 detections. And the vast majorities are spatially resolved. And this just shows a tiny snapshot of what WALLABY will be able to achieve in the coming years. Thank you.
Thank you very much, Tristan. That's a fantastic talk. Do we have questions for Tristan? You can either raise your hand or pop it in the chat and I can ask it on your behalf. Michele Capillari, go ahead and ask your question.
Hi, Tristan. Thank you very much for your talk. And I'm very pleased that we can do this joint talk and we have the opportunity to actually hear you guys from Australia. So thanks for doing this at a convenient time for us. So my question is, so you showed the asymmetry in the profile of that galaxy that you showed as an example, which agrees with the regime between the region where ram pressure dominates over gravity dominates. Did you look also at the asymmetries in the kinematics? Do they agree with that idea?
So you mean in this plot?
Yes, but in general, I presume you're doing for all galaxies.
I mean, so at this point, this was more a test case, just doing it for the one galaxy, but in future, we will be able to do it for all galaxies which are resolved. I haven't gone and looked, I haven't done the only kinematic analysis I've done was to derive a dark matter profile. I haven't looked at asymmetries in the kinematics of the galaxy.
Okay. Yeah, it would be useful to do it because, of course, in your picture, you expect the asymmetry in the kinematics to agree with the one in the morphology. Thank you.
Thanks, Michele. Other questions for Tristan? Perhaps I can ask one while we're waiting, Tristan. I was kind of surprised at the morphology of the galaxy that you studied, which is way out in the outskirts of the cluster, is so similar to one that's in the virialized region. Is that what you expect, naively? That galaxies are still getting ram pressure stripped in the central regions?
Yep. So I'll go and note that for the phase-space diagram, the different regions, like particularly the virialized region, it works in a statistical sense. So galaxies statistically that lie within this region are virialized, but it's not to say every single galaxy that lies in this region are virialized. So in this, particularly as the red square lies right near the edge, it's likely still on its first passage through the cluster. And similarly, we have down here a couple of these rather symmetric galaxies which lie fully within these virialized region, and yet they are rather symmetric, and also their H1 is extended well beyond the stellar disk. So if they were virialized, you'd expect them to have been significantly stripped. So it's more likely, like for these galaxies, that it's unlikely any of these galaxies are virialized.
Got you, thanks. Roger Davies.
Hello. And again, let me echo Michaela's remarks. It's terrific to have these talks, so thank you for arranging them. I wanted to ask you about projection effects and particularly the red square. and also looking at the picture, the slide that's up there, you've got those 3 points that are down below that you just mentioned you didn't think were virialized. The extent of the H1 is very similar in all these cases, right? Which surprised me a little, because one normally expects the H1 to be a bit more compressed when you get to the middle. And so that's interesting. I just wondered if you're able to make any comments about that. And also, of course, the problem of projection. You did, I think, show us the velocity of the one that's projected on the center. But because it's a problem, you used 1,000 kilometers a second, which is, of course, perfectly reasonable for the blue diamond. But it's a bit of a puzzle to know what to do about projection effects, right?
Yep. So to your first point, one thing to note with WALLABY is it's a blind survey. Probably should have mentioned that when I was introducing WALLABY, but it means that we're only going to detect things down to our sensitivity limit. So for the Hydra cluster, which is 60 megaparsecs away, it means our sensitivity is roughly in H1 mass of 10 times, 10 to the 8.3 solar masses. And as a result, we're only really going to be detecting things which are, we're unlikely to detect anything which is truncated, which is actually something I'm finding from further work I'm doing, which is now actually using the entire 60 square degree sample, which there's maybe 1 or 2 galaxies which might be on the beginning to be truncated, such as the red square here. But for the most part, we are going to be detecting those things which the H1 does extend further out. So that's probably a selection effect of our sample. Right. And then projection effects, yes, they are definitely something that come into it, and it's something that we can't go and disentangle the projection effects.
You probably need to somehow simulate the effect and compare what you have with what you expect.
Yes, yeah, that's probably exactly what we need to do.
Well, thank you, Roger. With that, unfortunately, we're out of time for questions, but I'm very sure that Tristan will be happy to answer any further ones by emails.